We'll get started. Today, we are going to move into the last part of the course, which is on control system design and observer design. So this is chapter 9. So we don't really have too many topics left. I think there are three broad topics that I want to talk about today. We'll be talking about controller design. Next class, we'll be talking about controller design for a specific eigenvector uh, requirement, and then the last topic would be observer design, and then I'll probably bring together all the concepts that we have studied in the context of this class and try and understand how do we design controllers for linear systems. I think the if there are any specific topics you would want me to cover, then I would greatly appreciate your feedback so that I can cover those topics in the class after all the required topics are over. If not, then I'll comment a little bit about how do we go from continuous time system to discrete time system, and then do controller design for the discrete time system and so on. So I know that this particular book has both discrete time and continuous time systems, but most of the time we are studying the continuous time because that's what the syllabus says. And the discrete time system also follows very similar ideas. So I'll probably just give you a overview of how do you translate concepts from continuous time systems to discrete time systems and vice versa. So hopefully that will be beneficial. And if there are any other topics you want me to cover in the class, I'll be very happy to cover them. There are going to be a few lectures cancelled. So next week on Thursday, I'm not available. I'm traveling. So I have to cancel that particular lecture. And then 3 weeks from now, I may not be available on Thursday, and 4 weeks from now, which is the last class, I may not be available on Thursday. So those are the three potential classes that I'm thinking about canceling. Next week is for sure cancelled. The other two classes, I don't know at this point of time whether I'll be canceling them or not. But I'll send you the email, so you will have the information available. Okay. So I want to start with an example of a linear system because I think so far we have done a lot of theory. It's time to go back to example. I know you have looked at some of these linear systems example in your assignment, so you have some idea of what are the real world linear systems. But today I want to talk about another such system. So I have a factory. I have a retailer, and I have a truck. That moves the stuff from factory to the retailer. And X1 is the factory stock, X2 is the retailer stock, and X3 is on the truck. So every day the factory has to decide how much it wants to produce, and then it ships certain amount of goods to the retailer, and then the retailer has customers, and they have a demand D that they want the retailer to serve. And so the dynamics of this particular system, it's of course a very stylized dynamic, but the dynamics is given by this is the shipped this is the percentage arrival of trucks, and then I have x3 dot t equals to alpha x1 t minus beta x3 t. So this is my linear system. So my A matrix is, can someone tell me what is my A matrix? And the dynamics is x dot t equals to axt plus but and plus 0 minus 1 0 d. This is not controlled. This is not a control. This is an external disturbance. dt. D should be a function of t. Okay, ut is how many stuff you are going to be making in the factory at time t, and this is the dynamics that tells you the production, the storage of stuff in the factory, the amount of stuff on the road, and the amount of stuff at the retailer, where people are coming in and demanding the stuff. So this is the control system. Let's say you are the owner of this business. So you own the production facility, you own the trucking facility, and you also own the retail storefront. Okay, and you are serving the demand. What would be your goal for this control system? So you have a control system. Every day, your company has to decide how many items to produce. That's UT. What would your goal be? What are the goals here? Anyone a business owner here? Yeah.
You want to keep X2 as close as possible to demand without going under it, so that you're not wasting stock in the retailer.
So what do you want? X2 to be greater than equal to D?
What you produce at the factory should be as close as possible to that as well, so you're not overproducing.
So you want X1 of T to be close to 0? Okay. You are a business owner. Do you own a business?
No, but I took a whole bunch of business classes at the time.
Okay, good. That's evident. I think those are the two primary goals for most of the businesses. You don't want to have overstocking at the retailer's end, and you don't want to have overproduction at the factory end. So you don't want to produce too much. By the way, there is a terminology for it. It's called just in time delivery. Okay, so people in supply chain, if you talk to supply chain folks, they'll talk about just in time delivery, which means that you're not stocking too many things all over the place. Okay, so depending on the control problem, depending on the problem, you might have certain goals. Broadly speaking, the goal for the control system is generally three things. One is stability. The most important thing is stability. So typical goals. stability. The second goal for the control would be agility. I'm calling it agility, but what it essentially means is how quickly you respond. Quick to respond. And the third one would be the coupling dynamics, constraints on. These are a bit more complicated goals, by the way. So we might talk about we are going to talk about LQR probably in the next class. So we'll see a little bit of that, but but with these kind of constraint, things are a bit more complicated. How would you achieve? Okay, so let's talk about. Let's see if this particular system is controllable or not. What we are going to talk about in today's class is this whole stability and agility thing. It is very, very closely related to the concept of controllability that we talked about. Okay, so let's first think about whether this particular system that we talked about is controllable or not. So what's the controllability matrix? That's B, so 1 0 0, and A times B, so that's minus alpha 0 alpha, and then AB times B. What the hell is that? Okay, now I have to do the math. What is A times AB? This is what I have. Can someone verify if this is correct or wrong? Looks right? Okay. Is this full rank? Is this matrix full rank? Yes.
I think it is, but I have to prove if it is.
Actually, you don't need a proof to say that it is full rank or not a full rank.
Oh, can you guys teach us determinant?
Yeah, definitely determinant is an easy way to do it. But the thing is that in this particular case, you don't even need a determinant. The way to see it is this one has 2 zeros, this one has 1 0, this one has no zero. So it has to be linearly independent, because these two, the sum of these two cannot be equal to this because you have a non-zero term here. So if alpha is not equal to 0, beta is not equal to 0, this implies controllable. So it must mean something. So what does controllable means? It means that you can go from 0 state to any other state. So you can go from 0 inventory here, 0 inventory here, 0 inventory here, to x1 here, x3 here, and x2 here. It's possible. You can do it. Right? That's what controllability says. And if you have x1, x3, and x2 here, and you want to wind it down to 0, 0, 0, you can do that. So you can start your business and you can shut down your business. Both of that is possible because the system is controllable. Okay, wonderful. When is the system not controllable? Let's think about the case where beta would be equal to 0. So what is beta equals to 0? Where did beta go? Oh my god. Okay, so this is beta x3 entering into the system, and this is alpha x1 exiting the system. So beta is equal to 0. What that means is that the truck cannot deliver to the store. When can that happen? When does that happen? When a truck is not able to deliver to a store. Natural disasters. So when there is a natural disaster, beta becomes equal to 0 because you cannot reach the store, you cannot serve the demand. What is the other situation? If there is a conflict, war zone, something like that, then beta would be equal to 0. So you lose controllability when beta is equal to 0. So when beta equals to 0, this term gets killed, it becomes 0. This becomes alpha square and minus alpha square, which is sort of a multiple of this particular column. So you lose controllability when beta equals to 0. What about when alpha equals to 0? When alpha is equal to 0, this term is 0, sorry, this column is 0 and this column is 0. So it's not controllable. Alpha equals to 0 means that you cannot ship stuff from factory to the store, right? So that's what alpha equals to 0 means. When would alpha be equal to 0? If there is a natural disaster at the factory end. Or if there is a war at the factory end. So right now, the Strait of Hormuz is blocked due to the conflict in that particular region. And so we have alpha equals to 0, and the price of oil has gone up across the world. Okay. So what's happening in the world is very closely related to what is controllable and what is not controllable. Okay. Some matrix has less rank than what was ideal for the world economy. Okay. So we lose controllability if something happens. So generally speaking, I mean, of course, this is a very stylized example, but it kind of gives you the idea that you can lose controllability if some fault happens. A few years back, my blower motor in my car went bad on a peak summer day. And so all four of us, like me, my wife, and my two kids, we were in sweltering heat, driving around the highway with our windows up and getting cooked inside the vehicle, because even though our compressor was working fine, air conditioning system was fine, the blower motor was completely off. And so we lost complete controllability of the system, and the cabin temperature was close to 95 or maybe 100 Fahrenheit. And we just had to deal with it until we got the blower motor replaced. So that's one case where controllability gets lost. If instead my refrigerant in my air conditioning system had leaked, in that case again I would lose controllability because my heat exchanger will not work, the evaporator will not work. So those are the situations where you lose controllability, and then you have to do something in order to restore controllability. Now let's assume that there is controllability. So technically speaking, I can apply a control signal which gets me from one point in the state space to another point in the state space. Okay, but at the same time, maybe I'm doing something like flying a airplane. So stability is important to me. So while I want to go from one point to another, I want to make sure that I'm always stable using the control signal, and I am probably responding very quickly to any wind gust or anything that is hitting the plane, because I want to make sure that the passengers are comfortable inside the airplane. right? So quick to respond. What about constraints on couple dynamics? So the way x1, x2, and x3 move due to an input or due to a disturbance, I want those to move in a very specific fashion. Okay, so that's how you couple the dynamics in a way that you can make sure that x1, x2, and x3 move in a certain fashion. So, for instance, in an airplane, you want to have decoupling between the lateral motion and the forward motion, or the motion in this vertical plane and motion in the horizontal plane. You don't want to couple the two dynamics, otherwise, your flight will go like this and passengers will be very scared, even if things are stable. Okay, so when people are when you are or if you are selling a very high end luxury car, $100,000 car, you want to make sure that the driver, if it hitting a road bump or if it is going on an uneven road, he or she must feel very happy that inside the cabin he or she is not feeling too much bump of the road within the cabin, right? So there are situations where you want to have constraints on the couple dynamics through your control strategy. So one of the very simple control strategy that has worked since the beginning of time is a linear control strategy, LTI feedback control law. So let me introduce that. Any questions on this before I jump on to the control part? So I have an LTI system, linear time invariant system, x dot t equals to axt plus but. For the time being, we'll assume that yt equals to xt. So I'm able to observe the entire state. Like I had mentioned in some of the previous classes, if you want to be able to observe the entire state, you have to invest a lot more in sensors. So you have to have a lot of money to sense everything. You have linear time invariant feedback control law. I am going to depart from the notation in the book, and I'm going to define the feedback law using this notation mu. You can use pi, you can use mu, but it cannot be ut. And this is f of xt plus rt. This is called feedback gain. And this is known as regulation signal. Okay, so my dynamics become, so closed loop x dot t a plus bf xt plus brt. There are lots of different variations of this type of control laws. So sometimes you want to have x desired minus xt. So so you kind of absorb that in the RT, and that's why you write the linear dynamics, the closed loop dynamics in this particular way. Now, uh, if your RT is equal to 0, so if you're not sending any regulation signal, then this becomes your closed loop A matrix. This is the closed loop system matrix. And so the question is, find F such that system is stable, closed loop system is stable. Question 2 is find F such that closed loop system has certain eigenvalues. And then question 3 is find F such that closed loop system has certain eigenvectors. And so we'll spend the rest of the class thinking about these topics. What does it mean for the closed loop system to be stable? We've talked a lot about stability. We have done some assignments on stability. What does it mean for closed loop system to be stable? Yes?
The distance to the origin, or wherever you're pointing toward equilibrium, it's always decreasing.
Right. So for instance, let's assume that RT equals to 0. So we'll forget about this term. So I have x dot t equals to a plus bf times xt. What is the equilibrium point? The origin, xt equals to 0 is the equilibrium point. So how do I know that the closed loop system would be stable? How do I know if this is a stable system? Forget about this term for now. Sorry? Negative real part of the eigenvalues. You can have complex eigenvalues as well. So the eigenvalue should have negative real part. So question 1 prime is real part of lambda I of a plus bf should be less than 0, or maybe it could be equal to 0 as well if you are only looking for the weaker notions of stability and not asymptotic stability. But generally speaking, in control systems, we are looking for asymptotic stability or exponential stability. So we want the real part of the eigenvalue to be strictly less than 0. Question 2 prime is my lambda I a plus bf. A plus bf should be equal to some lambda bar I. So I have picked a specific pole or a specific location on the complex plane, and I want my eigenvalue of the closed loop system to be at that particular point in the complex plane. So this is something that I have picked by control designer. What does it mean to pick lambda bar I in a real system? So if you were to decide on the suspension of your vehicle, you will go to a part store And then they'll say that, look, we have these 10 suspension systems. Which one do you want to buy? Right? What does it mean for you? What sort of lambda bar I would you prefer? Like that's what they are basically asking you. And different lambda bar I will have different price points. This is a $10 suspension system, and if you hit a road bump, you're going to be oscillating for like forever, right? And this is a $1,000 suspension system, and you won't even feel the road bump when you're driving on the road, right? And then there is everything in between. So by picking a specific point in the space as your eigenvalue, what you are saying is how quickly the system is going to respond. If the real part of the eigenvalue is very, very small, like it's closer to minus infinity, then you will respond extremely quickly to any disturbance, and every disturbance is going to die down very quickly. On the other hand, if your real part of the eigenvalue is close to the origin or close to the 0 point, then in that case you will have a very slow response to the disturbance, right? So if real part of lambda bar I is equals to 0 but is less than 0, no, I shouldn't say equal to 0, it's less than 0 but close to 0, sluggish response. If real part of lambda bar I is much, much less than 0, then you have fast response. And if, yeah, and of course, we don't want the real part to be greater than 0. When is a sluggish response reasonable? Passenger aircrafts. When is a fast response reasonable? Fighter jets. Okay. So depending on the situation, you are running a dishwasher, you want a sluggish response or a fast response. You're drying your dishes, you want sluggish response or you want fast response. You're cooling your cabin in the summer after you have left your vehicle in a parking lot for like several hours, you want a fast response. Yeah.
Is dishwasher a closed loop system?
Good point. You caught me. I don't know if it's a closed loop system or not. So okay. So there are two types of dishwashers. There are modern high-end smart dishwashers. Arguably they are closed loop. Who knows? And then there are like old dishwashers that are probably not closed loop. Okay, so my dryer, for instance, my clothes dryer, it has some sensing technology that senses the amount of water vapor coming out of the dryer, like the air, and so from that it senses how much more it has to run. So I don't have to worry about running it for 40 minutes. It just figures it out and then whatever closes the loop on its own. So that's a closed loop system for sure. But I think it has a sluggish response. So it's very slow. Let me think. My old car was a Toyota Corolla, and its air conditioning system had a very sluggish response. My new car is an Audi car, and it has a very good air conditioning system, so it cools the cabin fairly quickly. Okay, so that changes. That tells you like what the real value of lambda bar I looks like for different types of vehicles. So $20,000 vehicle, you will be in this situation as far as the cabin temperature control is concerned. But a $70,000 vehicle, you will be in this particular region. Okay, so it costs to place your pole at appropriate location. Okay, it's not free. Okay, what about Q3 prime? Q3 prime is saying that not only I actually want the I want to pick not just lambda bar I also want to pick v bar I. I want to pick the eigenvector corresponding to the lambda I. Maybe this one may not be for all lambda bar I, but maybe for some lambda bar I, you want to be able to pick what the eigenvector should look like. Okay, so essentially, probably 95% or 99% of the control design is trying to do one of these three things in the increasing order of complexity. Stabilization is very simple and straightforward. Placing the pole is slightly more complicated, and placing the eigenvectors also is even more complicated. Okay, so this one is essentially the suspension system of high-end luxury cars. And I mean like $120K plus. I can't afford it, so I can't say for sure. But at least in their marketing collateral, they've said that they have adaptive suspension or whatever, and they are selling it in the market for 120K. Because many of you are working in Center for Automotive Research, hopefully you will go to some car company, you give me a 20% off coupon code for this high-end car, then maybe I can afford it. Okay. All right.
So,
Yes.
I'm not sure if I'll be able to ask the question properly, but what exactly is like the difference? Like, why would we go after selecting certain eigenvectors and, just selecting certain eigenvalues won't serve that purpose?
Right. So we talked about it, I think, before you came. So there was question 3 here, the goal 3 here. And the goal 3 was you want to couple the dynamics in a certain way so that if, for instance, in a flight setting, if you apply a control strategy, it only applies on the flight in the vertical domain, but it doesn't lead to horizontal movement. And in the other case, if you're doing some horizontal control, then it doesn't apply in the vertical, like it doesn't lead to a vertical motion within the flight.
We want to confine the response of the
You're looking to confine the response in a very, like for a specific type of control action, you want to make sure that it responds in a certain way so that you're decoupling all the other modes in the system. Any other question? Yes, please.
So for scenario 3, is that going beyond like controllability and reachability, or is that more like you actually want to pick the trajectories that, like, for example, like
extremely good question. So I'll get to it in a bit, but we are actually going to cover some of those results. So you require controllability for this. In fact, what will happen is if your system is controllable, you can do 2 and 3, but you can't do 1. Okay, so you cannot stabilize the system, but the system may have inherent stability. So you will try to exploit that inherent stability in order to do things. So we'll talk about it in like 30 minutes. This one, you don't just require controllability, but you also need something beyond controllability to be able to specify the eigenvector as well. We'll talk about it when the time comes. This one I think we'll cover next week on Tuesday. These 2 things is what I'm planning to cover today. Okay. Any other question? So you need multiple actuators for you to be able to do this. Okay, that's just the main point. I want to partially address that question. That was anyway something that I wanted you guys to think about. What's the dimension of F? can someone tell me what is the dimension of F? F should have m rows and should have n columns. So U equals to Fx, right? So F should take as input x and give an output U. So F is an m cross n matrix. So the total number of free parameters to pick is Mn. I have Mn free variables that I can pick within this matrix. How many eigenvalues the system has? It has about n eigenvalues. And how many eigenvectors will it have? It'll have n eigenvectors or generalized eigenvectors. So that's n square variables. So you have mn variables that you can pick, but you have n square plus n different things that you want to set. It's quite likely that you won't be able to do that. Okay. So with n free parameters, with mn free parameters, you can probably influence mn of these things. So probably you want to pick n eigenvalues and then m minus 1 eigenvectors or something of that particular order. So it would be unreasonable to think that with mn parameters you can actually pick n square plus n number of things, because generally speaking m could be much smaller and n could be much larger. But that's just a hand wavy thing. We'll make things a bit more concrete as we go. Okay, so what is theorem 9.2 in the book? A be controllable if and only if lambda I a plus bf equals to lambda bar I can be picked for all I. I do want to make a small comment here that you have to keep in mind that complex, you can have real or pair of complex eigenvalues. So either all lambda bar i's are real, or if you want to pick a complex eigenvalue, then you have to pick the conjugate of that complex eigenvalue as well. So AB is controllable, then if and only if there exists an F such that the eigenvalues of the closed loop system can be picked arbitrarily. I'm going to prove the other way first. The forward thing I'm going to prove in a somewhat convoluted fashion, because I'll come up with the specific f that allows you to place the poles or place the eigenvalues of the closed loop system. But the other way, I think I can do it in a more general setting. So let's look at the proof for this part. So I can do a similarity transform. So, okay, I'm going to use proof by contradiction. So assume f exists such that lambda I equals to lambda I bar and AB not controllable. I'm going to assume that such an f exists. I have a gain matrix such that I can place the poles of each of the eigenvalues arbitrarily, but my AB is not controllable. So from AB, I'm going to use Kalman form. A hat, B hat. Can someone tell me what was the Kalman form for A hat, B hat from previous lecture? Perfect. So I transformed the system, did a similarity transform for the system, and I put it in the Kalman form for the uncontrollable system. And let's say f is equal to, let me do f hat 1, f hat 2. So I'm going to do the similar, I'm going to design a controller for this particular system. Yeah. What's the closed loop system matrix looks like? What is a hat plus b hat f hat? Anybody wants to try? What is determinant of lambda I minus a hat plus b hat f hat? If you do the calculation, it will turn out that is, this is determinant of lambda I minus a hat 1 1 plus b hat 1 f hat 1 multiplied by what do you notice? What's happening here? This f hat 2, this thing is not affecting this matrix at all. So a hat plus b hat f hat, no, it actually is affecting it. Okay, so it is affecting this particular part. But if I look at the determinant of this matrix, because it has this upper block structure, so this block is equal to 0, the determinant of this matrix is going to be determinant of the top part, this part, and then multiplied by the determinant of this part. So this part does not appear in the expression for the determinant, right? And the eigenvalues are determinant of are roots of this particular determinant, right? So this is a polynomial, and the roots of the polynomial would be the eigenvalue for the closed loop system. Anything unusual that you notice here? This determinant depends on f1 hat, so I can influence the eigenstructure of a hat 1 1. I cannot influence the eigenstructure of a hat 2 2. Okay, so the eigenvalues corresponding to this particular subpart of the subsystem is actually not going to change because of my action, because of my feedback law. So consequently, I cannot pick eigenvalues corresponding to eigenvalues of a hat 2 2. I cannot move the eigenvalues of a hat 2 2. In particular, I arrive at a contradiction that I was able to pick all the eigenvalues of this matrix, closed loop matrix. Remember that because I'm doing a similarity transformation, the eigenstructure of the closed loop system would not change for an appropriate f. Okay, so if I'm not controllable, I cannot pick all the eigenvalues of the matrix. But then you want the system to be stable. If you want the system to be stable, you want to be able to pick eigenvalues that have negative real part. So what kind of systems would be inherently stable, even if they are not controllable? If the eigenvalues corresponding to this part has negative real part. And that is called stabilizable systems, and I'll define it very soon. And remember, you had done this stability exercise in the context of phugoid motion of aircrafts. I know some of you have done that assignment, some of you are taking it for audit, so you may not know it. But essentially, that's inherently stabilizable, because even if you cannot control certain part of the system, the eigenvalues are negative. So system is stable. So the corollary, there are two corollary. One corollary, which is that eigenvalues of uncontrollable subspace cannot be changed using feedback law. And the definition 9.5. AB is called stabilizable if and only if all uncontrollable eigenvalues are stable. So what we have arrived at is no matter what controller I pick, I can only influence the eigenvalues corresponding to this block. I cannot influence the eigenvalues corresponding to this block. And my hope is that those eigenvalues are stable eigenvalues, which means that the real part is strictly negative, or the Jordan block associated with zero eigenvalue is 1. And so all uncontrollable eigenvalues are stable. Okay, then we call the system stabilizable. It means that there is some notion of like it's not controllable, you can't control it, but there is some inherent stability within that particular system, and hopefully that will come to your rescue in case things go haywire. Okay. Remember that in this entire discussion, I am not talking about actuator saturation at all. Okay, and actuator saturation is real, but for what it's worth, linear system theory doesn't worry about actuator saturation. And if you have actuator saturation and you still want to make sure that the system works appropriately, you have to take the 5500, the optimization class, where we talk about some of those techniques. Okay. Any questions so far? So this tells you what the goal for this particular exercise was, that just because you are uncontrollable doesn't mean that hope is lost. Being uncontrollable, if you're not controllable, there are certain eigenvalues you can move. So hopefully if the unstable eigenvalues are in this particular domain, then you can change it through the control strategy. And whatever is the uncontrolled part, it's inherently stabilizable, it's inherently stable, so therefore you don't have to worry about stabilizing those eigenvalues. Yeah. Okay. Now we'll talk about eigenvalue assignment by state feedback. So any questions so far before I erase this part of the board? Okay. So now my goal is that, okay, for uncontrollable eigenvalues, I cannot control it. So let's talk about this part. Let's talk about the part that is controllable. Let's do eigenvalue assignment for this particular part. So the goal now is, given that I have a matrix A and B that is controllable, how can I pick F so that the eigenvalues satisfy whatever we want it to be? So let's think about it. So my goal is eigenvalue assignment in controllable systems. So I have A be the setting Okay, so let's go back to 1950, 1960 maybe. I have a controllable system and I give you this problem as a research problem in your PhD. So I have a controllable system. I want to pick the gain matrix F such that I can do the eigenvalue assignment. What would be your step one? What would be your first approach? The simplest approach. Any thoughts? Yes.
I guess at the very least, pick easy eigenvalues to try and get to, so try and set them all to zero by working from that determinant equation we had on the.
So this equation doesn't apply. We are just focusing on this block right now because this block is controllable. Remember, this block is uncontrollable. This was for the uncontrollable system, so I don't care about this block now. I just want to do eigenvalue assignment of this particular block because that's what I can control. So you had some thoughts?
Well, okay, so I was wondering, I guess the first step would be you didn't know it was controllable, right? To prove it was controllable or not.
Sorry, can you say that
I
again?
was going to say the first step would be just to check if it's controllable.
Yeah, I'm assuming that it is controllable, right? So if it is uncontrollable, I have converted it into this format. So now I know that this part is controllable and I want to do eigenvalue assignment of this particular part.
Well, since you said it's the 1950s, we probably don't have like computers then.
Right, we don't have computers then. But maybe these are like 10-dimensional systems, so you can still do something about it.
I was going to say, there are like specific canonical forms you can use, like controller canonic form.
Right, we talked about it in the previous class. So we'll talk about it, but it's a bit complicated to go there. I think there is a simpler version for doing that, which I want to see if anybody wants to think about it. It's a brute force sort of version, simple idea. So let's define alpha desired, not S, lambda is equal to lambda minus lambda bar 1, lambda minus lambda bar 2, lambda minus lambda bar n. And what I get is a polynomial lambda raised to n plus d0, no, dn minus 1 lambda n minus 1 d0. So these are the coefficients. These are the coefficients of let's do determinant of lambda I minus a plus bf and this would be lambda raised to n plus g n minus 1 as a function of f So this term, whatever term you get here, would depend on f, because that's what you are picking. And then the question is, find f such that gk of f equals to dk for all k in 0 to n minus 1. Okay, so I look at the coefficients of this particular polynomial. I look at the coefficient of this particular polynomial. I want the two coefficients to be the same, in which case I have done the eigenvalue assignment successfully. So I want these two things to be the same for all k, and I have to find a matrix F that satisfies this condition. Now the question is, how do you solve this problem? How would you solve this problem? So I have all of these things are real numbers, dn minus 1, dn minus 2, all the way to d0. This is also real valued functions of f. I want this to be the same. How would you go about solving it? Any thoughts? Yeah.
I believe if we can say that F is an invertible matrix, can we not just move F to the other side because we are the ones who are setting our desired eigenvalues and evaluate the matrix?
So F need not be an invertible matrix because this is an m cross n matrix, and m and n could be arbitrary. But the way to generally solve problems of this type, it's called root finding problem. And the way to solve it is you convert it into an optimization problem and solve that optimization problem. So you can convert it into min of f in R m cross n gkf minus dk absolute value square summation k equals 0 to n minus 1. Now you can solve it using gradient descent, or you can solve it using Newton's method, or whatever is your favorite method to solve it. Okay, not an easy way to solve it, but this is a brute force way to solve this problem. I think it might work for like a 1 or 2 dimensional or 3-dimensional system, but I don't think it will work for very complicated systems. I mean, maybe it can work, but yeah, I don't know. It's just too complicated. Okay. Now the simple idea is gone. Now we need to look for a more complicated idea. So I'll take your suggestion and I'll convert the A and B into the controllable companion form. Okay. So this was idea number 1. Let's look at idea number 2. AB so I can do the controllable companion transformation and I can get A matrix in A hat matrix in the format. Do you remember what the controllable companion format was? For the time being, let's assume that U is in R1. Okay, we talked about it in the previous lecture. So if U is an R1, what's the controllable companion form? Should be in your notes from Tuesday. It's 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0. So off diagonal, upper half diagonal entry is 1. And then in the last row, the entry is minus alpha 0, minus alpha 1. And I want to make sure that I have noted it correctly. Right. So these are the, let me remind you what is this. So determinant lambda I minus A equals to lambda raised to n plus alpha n minus 1 lambda raised to n minus 1 plus alpha 0. And the matrix B was 0, 0, 0, 0, 0, 1. B hat, sorry, this is B hat. So AB is controllable, U is single dimensional. I can apply a similarity transformation to get this A hat and this B hat. The procedure to get the similarity transformation is there in the book. But in today's world, there is a package for everything, and so there is a package that can convert a matrix into a controllable companion form. Okay, so I have this matrix. Now let's look at A hat plus B hat F hat, which is whatever this is, and then minus alpha 0 minus alpha 1 minus alpha n minus 1 plus 0, 0, 0, 1 Fn. You know what? I'm going to make it go from 0 to n minus 1. That just makes things easy. Okay, I want this A hat plus B hat F hat to have a very specific eigenvalues. And if you recall the characteristic equation with those eigenvalues, where d0, d1, d2 all the way up to dn minus 1, so I have minus d0 equals to minus alpha 0 minus f0 what is f0 then? Alpha 0 minus d0. Right, so we found out what f hat looks like. Now I need to pull this particular linear policy back into the original space. So let me remind you that we had anyone remembers what b hat is? Is it bq or is it b q inverse b? Q inverse b? Okay. So if I pick my f to be no. Okay. If I pick my f hat to be, this is not there in the book, so we'll have to do some trial and error to be able to figure it out. So if my f hat is f q inverse, so then what is my a hat plus b hat f hat? It's q inverse a plus pfq. No, I want it to be f times q. Okay. So this matrix would become a similarity transform of a plus bf. So it will have the same eigenvalues. So I have to pick f equals to f hat q inverse. Okay, so for a controllable system, the way is if you have a single input, then the way to go about figuring out what is the f hat that allows you, or what is the f that allows you to do eigenvalue placement, is to first convert a and b into a controllable companion form using the matrix q. The q matrix is given in the book, but I'm sure you can find packages that do it now in Python. So you figure out what the matrix Q looks like that converts A and B into this particular form. Now, from this form, we were able to actually do things by hand in order to figure out what is this f hat that allows me to do the eigenvalue placement for A hat plus B hat f hat. Now, I need to pull this f hat into the original system. So how do I do that? I want my A plus Bf to have the same eigenvalue as A hat plus B hat f hat. So I wrote down the expression for A hat, I wrote down the expression for B hat. I hypothesized that my f hat should be of this particular form. And then I did the summation A hat plus B hat f hat. Turns out that this one is a similarity transform of A plus Bf. Similarity transform doesn't influence the eigenvalues of the matrix. So the eigenvalues of A plus Bf, if my f is equal to f hat q inverse, is the same as the eigenvalue of this particular matrix. And this eigenvalue is exactly what I wanted, because my d0, d1, d2 all the way up to dn minus 1 was the desired coefficient of the characteristic polynomial. So that's how you do the eigenvalue placement for a controllable system. You can apply the same procedure for a system with multiple inputs, in which case this b hat will have an identity structure in the bottom, and then you can apply somewhat similar idea to be able to do the eigenvalue placement. I'm not writing that down because we are out of time right now, but it's there in the book. I'll cover it in the next class, and then we'll talk about eigenvector assignment as well. So we'll do eigenvalue assignment, we figured it out, and then we'll do the eigenvector assignment, and that's how we'll complete the talk about the linear controller design. And then we'll talk about Riccati equation and linear quadratic regulator problem. So thank you so much, and I'll see you on next week, Tuesday.